So these two new soil orders, these artificial soil orders, are anthrosols and technosols. So we're going to go through the first one first. The second one's more relevant to our urban environment. Anthrosols basically means that extended human development over time has altered it uniquely from its native soil. So here we've got this picture of farmland. Basically what we're saying is like you can really tell what's been affected, right? I mean everything, these nice clean lines show that there's been specific things done to these specific sections. So what that typically involves is plowing, or wow, okay, they both come up at once, or this is applying fertilizers, or irrigation. These are all things that even if, temporarily across some section, it's not that big a deal. But when you're doing it for a long time, for an extensive place like this, this is no longer whatever soil it used to be, right? The climate of the area, irrigation is not climate, so the climate of the area would not affect the soils like this irrigation has. And especially when you're talking farmland, a place that's been in development for decades or centuries, then these alterations make a big effect upon the soil environment. Here's another way to picture anthrosol development. So let's say we have natural soil order. This is just, let's say, that chunk of farmland that we saw this last time. If this picture was kind of oriented up a little bit to where now we're looking at it from the top, this is kind of how you would see a soil order map. Things are kind of, they've got these different lines of distinguishing different soil orders, and then they've got numbers for this is a certain type of soil, this is a certain type of the soil, and so on. So originally, this is the native soil, right? There's a handful of different types, probably all mostly within the same soil order. What we see as farms are developed is that change that we talked about last time. Now, let's say these 4 farm fields have been emplaced. So what we're starting to see is that they're going to be managed differently than these native soils. These native soils are subject to natural forming factors. Here, and here, people are growing corn, soy, alfalfa rotations. And so they're, amending with fertilizer and irrigating it and that kind of thing. And so a certain effect is happening in these very specific regions that's not occurring over here. And then this one, maybe this is pasture, maybe this is beef cattle or something. And so it's subjected to very intense pressures that are still different from the natural phenomena, but also different and distinguishes it from these other farm fields. And so this is why we're seeing this power of anthrosol development across time. When certain regions start being managed differently than their natural environment, they start changing. And especially when we talk about land management that differs from one another but extends across a great period of time. These small differences that are happening in the first year are bigger in the second year and are really big and pronounced 100 years from now. If this has been 100 years of cattle grazing, this has been 100 years of corn, soy, they're going to be very different even though they used to be much more similar. Now when we get to technosols, here we're no longer really talking about humans affecting the soils so much as humans more or less creating the soil. So I'll make a similar soil map. So again, we have, let's say, a soil region, and this is the site of a future city. And so first, like, a little house gets built here, the very first house. And then slowly it builds up and builds up. The first thing, remember, is the soil sealing. So just being in an urban environment, what we're seeing is just streets being built everywhere, pavement everywhere, all kinds of asphalt, sidewalk, all sorts of stuff. So that's the first thing, right? So first we've got streets crisscrossing everywhere and already chunking up the land. Kind of similar to how we started having this. So it's showing, even if a whole person gets all this land, they're probably going to stop at the edges of the street. It forms natural new barriers where these used to be soils that kind of merged across each other. Now a street is here, it's not moving, and so it's making sure that what happens on this side is almost guaranteed to be different than what happens on this side. Next step is you need someone who's looking to manage the soil. But if it's all paved over or built on or something like that, we've got all these houses all over the place, and you're just really stuck looking for land, what you're probably going to be doing is building some of your own. And so you're going to install something here on a rooftop, or you're going to build something here above a brownfield or something like that. And so the important thing here is, like, watch here. Like, they used to be a similar natural soil order, and then they started changing it by adding fertilizer or whatever. And so that's a top-down, slowly, these sections are being changed from this one, from the top down. Here, there is no top-down because there's no connection. And so what we're going to see is, like, let's say that they can be filled with different content. So as you can see, even if you follow my patterns, even if they share the same base material, this one has 3 total layers and only shares 1 material type with this one, which has 4 material layers. And so this is something very common with Technosols, is that they are built synthetically, one bulk addition of material at a time. And so we have, first we fill to there, then we fill to there, then we fill to there. And so it's very layered, like a lasagna. And so that also introduces a lot of potential for complexity and diversity, because as you can see, just one other installment of another Technosol can be very, very different. We're installing not only more kinds of things, but different kinds of things. I mean, it's crazy. Technosols can be all sorts of things, and it's got next to nothing to do with the native soil. It doesn't matter what it was built upon, because it's being built there. Like Technosols themselves, they are dominated by their materials being of technical origin. The technical components of these Technosols is typically their liner, whether it be some constructed bed like concrete or wood, or some geotextile type thing. It's delineating this new soil from the native environment. And so that liner helps make sure that the Technosol developing in this container is different and separated from however this natural soil is developing. The other technical pieces of a Technosol are the inputs. So not only could they have synthetic inputs, like sometimes there are non-natural things put in there to facilitate some purpose. Like some Technosols are created as green roofs, and they need high drainage, so they actually have a plastic matrix that goes through the soil itself, both to hold it in place against the wind and to improve drainage so that the whole roof of the building doesn't collapse from the increased weight of water retention. And then it could also be natural inputs, like some kind of compost or something, but typically the materials used for Technosols are some kind of concentrated natural byproduct. At best, it's kind of compost or shredded green waste, but a lot of times it can also just be some kind of other waste media somewhere else, be it just backfill or something from a plant. Like a lot of things used in Technosols are paper sludge from paper mills. It's these very strange things. Like it may be natural, like paper, is just cellulose, and so it's still natural, but that doesn't happen in nature, really. You don't get this enormous, foot-thick layer of concentrated cellulose material with some weird kind of liquidy stuff in it. But a Technosol, you might see that. With the high cost of Technosol creation, because you have to make the liners, because you have to input all these materials, they tend to be better managed, and so their soil development actually happens really quickly. There's even some references that you can read in the optional readings about modeling soil Technosol pedogenesis. And so pedogenesis is the soil development trajectory. Just kind of where is the soil, what's acting upon it, and where is it going to go. So this is the pedogenesis, is where is the soil going. And so with technosols, because of their high input costs, they tend to be well managed and they tend to develop rather quickly. And what that looks like is a couple of different things. First, technosols tend to have higher biological activity. This is often because the things are artificially enriched because there is some intent to grow some kind of plants there, and so there's a lot of food for the soil microorganisms. There's also quick horizon differentiation. So these layers of soil are the horizons, and so it's quick in a technosol not only because it is installed in layers, and so it already has some pretty obvious horizons. It's also quick because this high biological activity stimulates quick reactions depending upon the different characterizations. And so what's going to happen is maybe this gets mixed a little bit here. This part gets quickly exhausted out of nutrients and whatever, and then so there's some mixing here. And then this never ever moves. And so now we see some, even after we already had some basic horizons, now we have, another set of horizons. We have this horizon, we have this horizon, this horizon. So we've kind of increased the number of horizons that we have. And this is one way that you can measure a soil's petagenesis, measure how much it's developed, is how strongly are the horizons differentiated from each other, how many horizons do they have. Not necessarily, but this is definitely a telling indicator. So the petagenesis of a technosol is unique to a technosol. All soils have a development trajectory, things which act upon them and move them in a certain direction. But with technosols, certain things are happening, kind of a meeting of a lot of coincidences, I guess. And so part of it would be the same time that we are starting to create these soils coincides with a generally favorable global climate. It basically means that we're not in an ice age. And so, since we're not in an ice age, it's generally warm enough for things to develop, because one of the great things that does develop a soil, it causes this differentiation of horizons, is biological activity. And biological activity is controlled by temperature. A lot less biological activity, especially in the soil when you're talking about the ice age. Something else is that these materials which are put into these technosols are typically very chemically reactive. So this means that they're ready for development right now. That they're going to decompose into different things pretty quickly, and that decomposition is going to be fuel for this biological activity. And so we're seeing hand in hand not only chemically reactive materials, but also, of course, following that is this high biological activity. And then something which I missed talking about earlier, but when we're saying low erosion, technosols typically don't have very much in the way of erosion because, again, they cost a lot of money, it's a lot of money to make a technosol. And so what happens is that people typically, first they'll make this bed, they'll fill it with highly chemically reactive material, like really good compost or whatever, because they really want to grow things. And then after they've made this bed, they protect it somehow. Usually they're covering it. Sometimes they'll put hoops over it. Maybe it's for the crops or not. And then, but ultimately what's happening is that rainfall is being protected from this area. The material, since it is encased inside within the frame of this bed, it's got nowhere to run. And so low erosion counts, and with low erosion, a soil can develop. If a soil was eroding, if all this stuff was running out, then we just wouldn't, eventually we just don't have a soil left to develop because it's all eroding away. Bam, there's no petagenesis because there's no soil. There's no soil development because there's no soil. And so keeping your soil particles where you want them, having them within a bed, somehow constrained, protected against erosion, and keeping the material here is one way that you get rapid petagenesis of technosols. All right, we're going to take one more look at a constructed technosol just to examine a couple more points and we'll move on. So I want to relay something that Hafiz et al. Found or documented in 2012. They investigated this layering of technosols, and they found that with increasing depth, just going down the soil profile, they found decreasing bioactivity. Basically something kind of like this. You have the most biological activity on the top and slowly decreasing as it gets toward the bottom. Maybe it should have been more, maybe a more gradual arc, something like that. It doesn't matter, whatever it was. Highest biological activity at top, lower at bottom. And this is pretty classic. This is what you find in natural soil orders as well, is that most of the food for biological activity is is contained in organic matter being deposited, be it leaf litter or something like that, falling to the top. And so most of the stuff that lives there is going to be up near the top where all the food is. Something else that they did find, though, is that due to this layering, they found distinct genetic fingerprints for different microbial communities as they went down the soil profile. So not only were the most of the activity in the top branches, but also the distinct communities, like there was X, Y, and Z here, but then there was just X and A here, and then there was only B, and then there was C and D here, or something like that. So on one hand, technosols act like natural soil orders. Biological activity decreases as you go down. But on the other, they reflect the filtering aspect of the urban environment itself, right? In the urban environment, things have to come from nature and work their way into the urban core. Similarly, here we have these filters. If all the bioactivity is starting from the top, stuff is falling out of the air even, yeast or bacteria or whatever is falling out of the air and landing on the soil, fungi, something. They are colonizing this area where most of the food is, but there's a hard filter. As this changes, as the substrate changes, as the media changes, not everything is able to move on to the next realm. So a bunch of stuff shows up, right? We've got this big thick arrow shows up, but then we see that it's a bit thinner when it goes down, and then it's a bit thinner when it goes down, and then it's kind of quite faint. So two things happening, right? In the very bottom of a technosol, very low activity because there's low food, and then even lower activity because of this filtering effect. All right, one last part about petagenesis. When it comes to technosols, as we've seen, humans are creating them, and thus the intent that we come into it with really dictates what happens with these technosols. And so generally, artificial urban soils, technosols, follow kind of one or two paths for petagenesis. They're either typically kind of decorative for parks or something like that, in which case, really, there's a surprising amount of sand in these soils. It's basically all sand. Some research by a colleague of mine, Neil Bell, has assessed a lot of green spaces of technosols in the Portland area, and their sand levels are just astronomical. Like most of them, about 80%. It's hardly really a soil. It's a sand, really. It's almost like they're planting trees into a playground sandbox. It's not really the greatest. Then the other end is for productive use. This goes to the other extreme. This tends to be incredibly high in organic matter and also tends to receive fertilizer inputs. And this came from my research, basically just looking into urban gardens, urban created soils, urban technosols, and be it in-ground or raised beds, the organic matter was pretty intense. Like I think the average was something, I want to say 13%, when most agriculture suggests, something like 4 to 6%, depending on who you ask. So my average was twice the upper range, and I even had my highest report 33%. Basically, like this is straight compost. It's 1/3 carbon, on 1/3 organic matter. This is crazy. These plants burned and died before the end of the year. So you can see these very, very different, depending on what someone wants to do with it. They're either trying to get it as cheaply as they can because it's just supposed to be some amenity for something else, just some green space slapped on the side somewhere. Or they're trying to make something of it, and they kind of go overboard because, again, remember, we can affect everything incredibly strongly. This, us, right here. And so it's really easy to affect whatever you want and to make something incredibly rich if you'd like. And so this shows the differences in technosols. You can have basically a sandbox, and you can have basically a compost box, and they would both be considered technosols because they were created soils. All right, so that's it. Thanks for sticking with me. Here you can see a technosol created on a rooftop in Portland. And so this kind of brings in some questions of like what makes a soil or not, what makes a technosol. Right? That's not connected to any parent material. And so the same question, I put this question to you as just like a thought experiment. Would a potted plant be a technosol? I've put everything into that pot, and it's not connected to any parent material. I've created it. It was technically made. So could a potted plant be a technosol?